Okay, so I think we can start. I welcome you all to Science Hub Talks, where we host different expert speakers. And today it is my pleasure to introduce Professor Lyatt Jaeglé from the Department of Atmospheric and Climate Science at the University of Washington. And her research focuses on atmospheric composition, air quality, and climate using different kinds of observations and computer models. And now she is a principal investigator of the STRIVE mission. So today she'll tell us about STRIVE, which is a NASA Explorer mission designed to observe a region on the transition between troposphere and stratosphere. So the floor is yours.
Thank you very much, Blanca, and thank you for this kind introduction and for the invitation to speak today. I believe is my camera working? Let's see.
Yeah, we can see your presentation, yes.
Okay, all right, okay.
Yeah.
So I'm truly delighted to have the opportunity to share the STRIVE mission with you, with this audience. So STRIVE stands for Stratosphere Troposphere Response using infrared vertically resolved light explorer. And it is a satellite mission concept that was recently selected as part of the Earth System Explorers program that NASA has. And STRIVE will provide daily, near global, high vertical resolution measurements of atmospheric temperature and composition throughout the upper troposphere and stratosphere. And we're really excited by all the science questions we'll be able to address with STRIVE because it represents a step change compared to current capabilities and will really transform our view of the upper troposphere and stratosphere. So over the past 5 years, I've had the privilege to work with really an amazing team with scientists, engineers, managers to develop this concept. And it is really the result of a collaborative effort across universities, government laboratories, research centers, and our industry partners. Our leadership team includes Jun Wang from the University of Iowa, who's our deputy PI, Luke Oman and Tom Anisco, who are respectively our project scientist and deputy project scientist, both at NASA Goddard Space Flight Center. Matt Delan is the lead for the Argos instrument. Charlie Bacon, our project manager, Charles Baker, our project systems engineer, and Rebecca Peters, our project application lead. Listed our fantastic science team here, our instrument developers. So the instruments will be developed by NASA Goddard with BAE Systems and STC, and our spacecraft provider will be Northrop Grumman. So today I'd like to tell you a bit about the mission, the science questions that motivated our instruments and our products, as well as our applications. First, a bit of background about NASA's Earth System Explorers program. So this is a new NASA program, and it's designed to address target observables that were identified as part of the 2017 Decadal Survey for Earth Science and Applications from Space. So that Decadal Survey identified a number of target observables and key science questions, and STRIVE addresses the need for vertical profiles of ozone and trace gases. And as I'll show, it goes beyond that, as it also provides observations of temperature, aerosols, and clouds. This is the Explorers program is a PI-led competition for medium-sized missions. And this was a two-step competition. STRIVE was one of 4 missions selected for Phase A concept studies in May of 2024. And recently, just a few months ago, in February of 2026, STRIVE was down selected to proceed to phase B. So we're really excited by these news. In terms of the steps moving forward, we'll have a confirmation review sometime in the spring of 2027. And if all goes well, a launch is planned for mid to late 2030. This is a 3-year baseline mission. So 3 years is basically the prime mission lifetime. But we expect the mission to last much longer, 15, 20 years if all goes well. But 3 years is the requirement. So we've all experienced the upper atmosphere firsthand, right? When you're on a commercial aircraft flying at 9 to 12 kilometers altitude, cruising altitude, you're flying right near the boundary between the troposphere below where the weather is and the stratosphere above where the ozone layer is. And the boundary between the two varies in space, but it sits at about 10 kilometers altitude. And STRIVE will focus on the upper troposphere and stratosphere. So the region roughly between 5 and 50 kilometers in altitude. And this region affects the surface in ways we don't always think about or don't always see. So the upper atmosphere modulates weather patterns and extremes that we experience, whether it's cold outbreaks or heat waves or atmospheric rivers. It controls how smoke, dust, and pollution travel long distances, affecting air quality far from their sources. And finally, it protects life at the surface from harmful ultraviolet radiation through the ozone layer. Now, this influence goes both ways. As surface weather can affect winds aloft. You have injection of pollution from wildfires or from particles from volcanoes that inject these particles or gases up in the stratosphere, affecting composition and the ozone layer. And in addition, the upper atmosphere is the region through which every aircraft and spacecraft has to go through, and where turbulence, icing, and ash create real safety hazards. So understanding this coupled system is really key to be able to predict our weather, protect our health, and ensure our safety. The upper atmosphere, however, is also a critical blind spot in our observing system. We don't observe it as well as we wish we would be able to observe this. And the challenge is that many of the important processes that control that region and these interactions between the stratosphere and troposphere happen on scales that are quite small. So tens of kilometers horizontally to a kilometer vertically. And these processes are shown on the top right. They include outflow from convective storms, volcanoes, or wildfires. They include gravity waves. They include cirrus clouds or stratospheric intrusions. And to be able to understand the effect of these processes, we need to be able to resolve them at their true scales so that we can understand their large-scale impacts. And today's observing systems have some fundamental limits. We have our high-altitude aircraft and balloons that provide these exquisite, high vertical and horizontal detail, but they tend to be snapshots in time and space. Complementing those, we have satellite observations, our LIM and NADER sounders that can provide a global context and global coverage, but often with insufficient vertical or horizontal resolution, so that we cannot resolve those fine-scale processes. And STRIVE will fundamentally change how we observe the atmosphere, as it will combine global coverage with 1 kilometer vertical resolution and dense horizontal sampling over 400,000 profiles a day. So I've watched this field evolve throughout my career. And so my very first project as a graduate student, we launched a balloon in the stratosphere right after Mount Pinatubo erupted, and we were really thrilled. We collected, 1 vertical profile with 3 data points, and it clearly showed the impact of the volcanic eruptions on stratospheric chemistry. Then in the mid 2000s, we started having observations from the microwave limb sounder on Aura, which provided that really beautiful, global view with vertical profiles of stratospheric composition. But with a significant trade-off, it had many vertical profiles, 3,000 profiles a day, but 3 to 4 kilometer vertical resolution, so blurring some of the fine-scale vertical structure. Now, with Strive, we'll have 2 orders of magnitude more profiles with 1 kilometer vertical resolution. So that, for me, that leap really shows how far the field has come and how powerful and exciting Strive will be. So with these new observation capabilities, Strive will allow us to address some long-standing atmospheric challenges. And in particular, Strive is designed around 4 key challenges, which map onto the 4 Strive science objectives. And our overall goal is to understand the processes that control the composition and dynamics of the upper troposphere and stratosphere, so that we can better constrain their influence on climate, the ozone layer, air quality, and weather. And those 4 challenges, first, it's convective and large-scale transport, so basically being able to track pollution, smoke, and ash impacts on air quality and mobility. Second challenge is the future of the ozone layer, so being able to understand the processes that affect the fragile and uneven recovery of the ozone layer. Stratosphere-troposphere coupling, we'd like to be able to constrain the influence of the stratosphere, both on weather and weather predictability, but also on tropospheric composition. And finally, climate feedbacks. We will reduce uncertainties in feedbacks associated with ozone, water vapor, and thin cirrus in the upper troposphere and lower stratosphere. So let me now walk through each challenge and show how Strive will address them. Starting with the first objective, to track smoke, pollution, and volcanic impacts. So, and this is about really connecting surface emissions to their global impact. So we know that storms and convection in storms lift pollution, smoke, and water vapor high in the atmosphere, where they can spread globally and influence downwind air quality as well as climate and aviation. One example of this is the summer Asian monsoon, where deep convection in the monsoon system routinely lofts pollution and smoke in the upper troposphere and lower stratosphere, and form this really persistent pollution layer that stretches sometimes all the way from the Mediterranean to the Western Pacific, and can linger there for months. We also have another example of this is, in the Western US and and in Canada, we often have every summer now these, very large wildfires that inject smoke high in the atmosphere, where fast wind can carry them across the continent and affect air quality thousands of kilometers downwind, as was the case, for example, last summer with pollution from Canadian fires affecting air quality in New York City. Now, the challenge is that we don't have the vertical information that we need. The limb viewing satellites will map the seasonal pattern of this convection and transport, but we'll miss the daily process scale transport. From nadir viewing instruments, we can see the total column, but without being able to separate surface pollution from upper atmospheric contribution. And our models struggle to capture these processes of convection and this large-scale transport. So we really need this missing vertical context that Strive will provide, that will help with more accurate air quality forecasts and improved smoke and ash routing for aviation, and just in general better understanding of the global dispersion of pollution. The second challenge is understanding the future and the recovery of the ozone layer. So the ozone layer is one of the most important feature of our atmosphere, as it absorbs ultraviolet radiation, and so it protects human health as well as ecosystems and agriculture from DNA mutation. Because of the Montreal Protocol, the ozone layer has been recovering over the last few decades. But we know that this recovery is uneven. We've seen recovery in the upper stratosphere, but in the lower stratosphere, some regions show continued decrease in ozone, and our current models tend to fail to reproduce this pattern. In addition, we've observed increasing disruptions of stratospheric composition, with frequent perturbations from wildfires, volcanic eruptions, and extreme polar dynamics. Shown in the top left, we can see the 20-year record of observations from NASA's microwave limb sounder on Aura. And what this shows is, as a function of time since 2005 and latitude, perturbations as shown in terms of standard deviation compared to the long-term mean of water vapor, HCl, and ozone. And what you'll notice as these colored circles are large perturbations, more than 3 standard deviation. And these tend to be clustered over the last 5-6 years. So, really the frequency and magnitude of these large perturbations seems to be increasing. We're seeing impacts of events like intense polar vortex perturbations, or the recent Hunga volcanic eruption that injected an unprecedented amount of water vapor, or injections of perturbations due to injection of smoke from wildfires. And these wildfires, in particular the pyrocumulonimbus smoke injections, seem to be happening more often, and we're just only beginning to understand their impact on the stratosphere. Shown on the bottom left is an analysis in a recent paper by Peterson showing over the last 10 years, those pyro-CB events and the maximum smoke injection altitude relative to the tropopause. And this shows that more than half of those pyro-CB events occur within 1 kilometer of the tropopause or higher. So they tend to have this large impact in a region where we know, if smoke is injected, it can stay there for a long time. And the effects on ozone are unclear at this point. In addition, we're also beginning to learn about new and potentially increasing future threats associated, for example, with space debris from satellite reentry. or the potential for stratospheric aerosol injection as a means to modify solar radiation. And so we have these very large, modeling and observational gaps, and these a looming data desert with models not being able to reproduce some of these patterns, and with aging satellites, as the Aura microwave limb sounder is expected to have an end of life sometime around 2028. So our ability to observe and understand these new threats is at risk. The third challenge centers around understanding how the stratosphere drives surface weather and tropospheric composition. So if we first, let's focus on weather. So if we look at forecast scale as a function of forecast lead time, we see that our short-range weather forecasts are quite good up to a week or so, and we have useful long-term outlooks where the predictability comes from sea surface temperature or El Nino. But in between, on the 2-week to 2-month time scale, our forecast scale falls off and is really low. So this is the sub-seasonal to seasonal, or S2S, predictability desert, as it's sometimes called. And this gap is a big issue, a big planning challenge, because this is exactly the window that people need for many critical logistical decisions, whether it's in terms of utilities or water managers or agriculture and disaster response. If we were able to have information weeks ahead, that would allow us to have, better plans for staffing, management of reservoirs, or prepare for peak energy demand or crop and irrigation decisions. And that's where we know that the stratosphere could help. So the stratosphere has, is a key source of predictability. Unlike the near surface weather, the stratosphere evolves more slowly and retains memory of large-scale disturbances. So circulation anomalies can persist and propagate downward over time. For example, if we have shifts in the polar vortex or changes in the winds in the tropical stratosphere and through the quasi-biennial oscillation, these shifts can propagate down, affecting the jet stream or affecting tropical convection, and precondition atmospheric rivers, heat waves, or cold air outbreaks. So this could provide us early warning weeks in advance. However, today's models do not capture many of these interactions between, the signals propagating from the stratosphere to the troposphere. And that's because we lack some of the vertically resolved observations that we need to understand the connection between the stratosphere and troposphere. And that's where we hope STRAB will help. In addition, exchange between the stratosphere and troposphere is a significant but poorly quantified source of tropospheric ozone. And it can affect tropospheric OH and surface air quality. And, exchange between the stratosphere and troposphere is also important for the budget of stratospheric water vapor as well as budget of methane. So vertically resolved observations from the upper troposphere to the lower stratosphere will be really key to be able to constrain this exchange much better in the future. Finally, our fourth objective, fourth challenge, is understanding the complex feedbacks that couple radiation, circulation, and composition in the upper atmosphere. So the upper troposphere and stratosphere is a key region for climate change. We know that there are clear signs of human influence in that region. We have faster tropical upper tropospheric warming than surface warming. We have strong stratospheric cooling, and the tropopause is rising. And all these changes initiate feedbacks that can be, further amplify these changes, by changing water vapor or ozone or cirrus clouds or circulation, then feedback into changing radiation and further affecting temperature. Now, these feedbacks are uncertain. An example of this uncertainty is shown on the bottom left, where we look at the stratospheric water vapor feedback. Models have a wide range of uncertainty in terms of the magnitude of these feedback. And so these amplifiers are really poorly quantified, and that uncertainty matters because it affects the reliability of medium and long-term projections that are used in climate for energy markets or insurance, water resources, and infrastructure. All right, so I've walked through some of these key challenges, and now moving to Strive. So, over the last few decades, key satellite observations of stratospheric compositions have come from limb viewing instruments because they provide this long path through the atmosphere, very sensitive to low abundance of trace gases, aerosols, and thin clouds. And the observations at different viewing angles provides profiles with good vertical resolution. Now, this works only down to maybe the mid to upper troposphere because lower down the atmosphere is too dense. And one of the downsides is that we cannot, with limb viewing observations, we don't have, we cannot reach very high horizontal resolution, and because it's limited by the viewing path through the atmosphere. So typically horizontal resolution is on the order of hundreds of kilometers, compared to nadir viewing observations, which have high horizontal resolution but measure total atmospheric column with little vertical information. So, and these limb viewing satellites come in different flavors. We have limb emission, such as the microwave limb sounder, that observe composition during day and night. We have limb scattering that are provide daytime only observations, and so there are no observations during polar night, for example. And then we have a solar occultation, which of those techniques tends to provide the highest vertical resolution and precision, but sparse coverage. As occultation is limited by the number of times you can observe sunrise and sunset, and that's typically yields about 30 profiles per day. In the last few decades, there's been really this long history of observations using all these techniques in the past, in the present, and moving into the future. And Strive will help fill that imminent data desert, for example, that was discussed in Ross Salowich's paper, providing measurements of limb emission, but also of limb scattering. So Strive will provide over 400,000 profiles per day. So in 2 months, Strive will deliver the same number of profiles that the microwave limb sounder did in 20 years of operations. It will have fine vertical resolution of a kilometer and dense horizontal sampling, tens of kilometers, so that we can resolve fine-scale upper atmospheric processes for the first time. And will provide comprehensive observations of temperature, trace gas concentrations, including ozone, water vapor, methane, nitrous oxide, CFCs, pollution tracers like CO and HCN, reactive species like NO2, nitric acid, chlorine nitrate, and 2O5. And we'll also have information on high altitude clouds and aerosols. So STRIVE will have 2 limb viewing instruments on a sun synchronous orbit with a 1:30 equatorial crossing time. We chose this orbit and this equator crossing time to match the long-term record of aura. And we'll have 2 instruments on STRIVE. The main instrument is ALICE, the Advanced Limb Infrared Chemistry Experiment. And then we have ARGOS, the aerosol radiometer for global observations of the stratosphere. The bottom right shows you a picture of the viewing geometry. So the satellite, which is a Leostar 2 from Northrop Grumman, will be on an orbit of about 800 kilometers. ALICE will observe the atmospheric limb about 3,000 kilometers away in opposite direction from the flight direction. And then ARGOS has 8 viewing angles, one of which is co-aligned with ALICE, and then they're separated by a 45-degree angle, and that will provide the more global context. Shown at the bottom left is the sampling of ALICE and ARGOS as a function of number of days and orbits. So in about 3 days, both ALICE and ARGOS will each cover about 75% of the Earth between 82 north and 82 south. And in 5 days, we'll have 90% coverage, which is really a large improvement compared to current satellite observations, such as MLS or the OMS limb profiler. So ALICE is the core science instrument of STRIVE. It is a Dyson imaging spectrometer that measures emitted infrared radiation from the limb. And it's the wavelength it observes are between 4.5 and 14.1 microns. So provides as its infrared emission, it provides measurements during both day and night. The instrument will vertically scan the Earth's limb, viewing the atmosphere with a 256-kilometer swath cross-track by 1 kilometer vertically. And we're using a scan mirror. It takes about 6 seconds to scan the atmosphere between the surface and 120 kilometers altitude. And over that time period, we'll collect 600 images with a spatial dimension and spectral dimension. And this vertical scan provides us with 200-meter oversampling, and that's how we get at that 1 kilometer vertical resolution. This wavelength region allows us to retrieve some of the products listed here on the top left. So from CO2, we get temperature. We get some of the other products include ozone, water vapor, methane, many trace gases. This is a rich infrared spectrum, so there are additional species that we could also retrieve with a science enhancement option, such as SO2, CLO, ammonia, PAN, SF6, and HCFC22. So we do these 6-second scans, and this is repeated as the spacecraft moves along. So that leads to a 40-kilometer spacing along track. So this is repeated every 40 kilometers, and across track we have 32 profiles with 8-kilometer resolution. So together that leads to 410 profiles per day with 1-kilometer vertical resolution. The technique and scientific heritage of ALICE comes from hurdles on aura, and but because we have enhanced spectral coverage and a broad swath, that leads to much finer cross-track resolution, faster, and we also have faster vertical scans, so that gives us this unprecedented detail. An example of what we would be able to see is shown here, bottom right, which shows a 3D view of atmospheric composition and temperature. And this particular example shows simulated ALICE gravity wave-induced temperature perturbation over Iceland. And you see the gravity wave with the horizontal and vertical dimensions of that gravity wave. Argos is a contributed instrument that will enhance the science. So Argos measures scattered solar light in two wavelengths, 870 nanometers and 1550 nanometers, and in 8 viewing angles, 8 directions as shown here. It's a small instrument. You see the dimensions on the left here. It's basically the size of my hand, about 20 centimeter in diameter and 11 centimeter, in height. It builds on the OMS limb profiler heritage, but because it has these 8 viewing angles, and it has faster sampling, so that it's much more sensitive. It has better spatial coverage, and because you're viewing, similar air mass from different viewing angles, for example, forward and backward, you have different scattering angle, which can give you constraints on particle size. Argos will yield 100,000 profiles per day with 1-kilometer vertical resolution and 20-kilometer spacing along track. There's currently a version of Argos that's flying as part of a technology demonstration that was launched in March of 2025. Shown on the right here is some of the global observations that Strive Argos would enable. So I should also mention that Argos products are shown in the left here, that are the aerosol extinction, angstrom exponent, radius, number density, and polar stratospheric clouds. So that coverage that's allowed by these 8 viewing angles is shown here on the right, and this is for 1 day of simulated Argos sampling of the 2017 British Columbia Pyro-CB smoke plume in the stratosphere. We can really track, especially at high latitudes, the horizontal extent of that plume. Looking at the what type of processes Strive will be able to resolve, we can illustrate this by taking the example of the Hunga eruption, which injected enormous amounts of water vapor and aerosols high in the stratosphere. So this figure shows the water vapor and aerosol plume 3 days after the eruption. On the left, you have a model simulation for water vapor and aerosol extinction at 26 kilometers altitude. And in the middle, you have the model as sampled by current instruments, MLS, SAGE-3 on ISS, the OMS limb profiler. And these instruments only gave us glimpses of this volcanic plume, as you can see, and sometimes entirely missed the plume because of the coarse horizontal sampling, as is the case for the SAGE-3, for example. Now, Strive will give us a new view, really. Instead of seeing these isolated snapshots, we'll see much better the horizontal and vertical structure of the injection, and we'll be able to follow how it evolves over time globally. So Strive will allow us to capture some of these volcanic wildfire and pollution plume structure with a lot of detail, which will help in terms of improving forecasts of their evolution and impact. Another quick example of some of the science and capabilities that Strive will enable is looking at tracking, convective outflow. This is an example of some observations that were obtained a few years ago as part of the ECLIP mission over Eastern Asia, flying in the Asian summer monsoon. So on the left, you have the flight track of the WB-57 in white. The green circles correspond to MLS observations profiles. So in over that region, there were 3 profiles, and then the black line correspond to the MLS, to the Strive, the Alice swath, 256-kilometer swath with vertical profiles across those swaths. So if we look over that region sampled by the aircraft and we look at profiles of CO and water vapor, we see that with Strive, we'll be able to capture some of these, enhancement of CO and outflow from the Asian summer monsoon, as well as variability in water vapor due to dehydration and hydration of the stratosphere after convection. So Strive will enable, a global perspective on process studies of convective outflow. There are many synergies that we're excited about with other atmospheric composition nadir viewing missions. For example, if we look at the current and future nadir viewing instruments, they measure total columns of ozone, NO2, methane, CO, and aerosols, both from geostationary and low Earth orbit constellations. And two of the key challenges come from, how do you go from these total column measurements to being able to separate troposphere and stratosphere, as well as being able to relate tropospheric columns to surface concentrations. So if we look at, for example, on the bottom right, the contribution of the upper troposphere and stratospheric columns above 10 kilometers altitude to total column abundance for ozone and NO2, the upper troposphere and stratosphere account for 80 to 90% of the signal. For methane, it's lower; it's about 20%. We can also look at how much of the variability in the column comes from the upper troposphere and stratosphere, and we see that for ozone it's very high. It's 80% or more. For methane and NO2, it accounts for up to 50% or so of the variability. So being able to really separate the upper troposphere and stratosphere from surface is really important, and Strive's limb profiles in the upper troposphere and stratosphere will help improve tropospheric composition and surface emission estimates from these instruments, through various techniques. Can be subtraction or data simulation of both of all these measurements, or combined retrievals. In terms of validation of Strive, we'll use a combination of routine, coordinated, and targeted validation. for routine validation, we'll take advantage of multi-platform observations of from balloons, aircraft, ground-based networks, and satellite missions. We'll have a coincidence predictor and partner with international networks to coordinate validation with ground-based stations, but also balloon launch site operators. And then we'll have a targeted post-launch validation with a dedicated balloon campaign for the first few months after launch to enhance profiles of ozone, water vapor, and temperature, and really try and target challenging upper troposphere, lower stratosphere feature to really validate our measurements. Finally, we're excited by the societal applications and benefits that STRIVE will enable. So STRIVE observations will be key to initializing and improving a wide range of models, whether it's water or air quality or AI-based models, and will lead to better forecasts from days to weeks in advance. And these gains in forecasting will translate into 4 clear areas of societal value. First, improved prediction of weather extremes. So supporting planning for agriculture, energy, water resources, and emergency response. Monitoring ozone recovery. So be able to track ozone layer recovery and understand its protection against harmful UV radiation. More accurate hazard forecasts. So helping both public health in terms of air quality, but also aviation safety for smoke, volcanic ash, and turbulence. And better risk forecasting, which will strengthen decision-making for long-term infrastructure investment or earlier warning for weather extremes. So STRIVE data will be essential for, to power the next generation of models that will lead to better predictions. So, this concludes my presentation. Thank you very much for your time and the opportunity to share this mission with you. I welcome any questions, and if you're interested in STRIVE science, synergies, applications, and would like to collaborate, we'd really love to hear from you all. So please don't hesitate to contact me or any of my team, such as June, Luke, or Matt. Thank you very much.
Thank you very much for your presentation. Do we have some questions? Maybe I can start. You were talking about synergies and validation. Have you considered EarthCare satellite, which is also able to observe stratospheric aerosols and get vertical profiles?
Yes, we'll certainly look at EarthCare. They're just trying to take advantage of as many observations as available. Yeah.
Other questions? Maybe I have another one. Regarding the forecasting, do you think that STRIVE data can be integrated into operational weather forecasting, assimilated into the model?
That's a great question. So for that, data latency is an issue. So our baseline mission for data latency, we anticipate having products within 24 hours, which is not fast enough. for the at least short-term weather predictions. We do have a science enhancement option that would enable much shorter data latency of 3 to 6 hours, which then it would be feasible to assimilate these observations. It would be for observations of temperature, water vapor, ozone, as well as aerosols. So that's for short-term, sort of for weather, short-term weather forecast. For subseasonal to seasonal forecasts, data latency is probably not quite, 24 hours is probably fine to initialize many of the more subseasonal to seasonal forecasts. But certainly is something that we plan on, pursuing with the NASA models, and would welcome, any European models to use Stripe data as well for data assimilation.
Yeah, great. Thank you. Other questions? We have one question in the chat. One question Scott Osprey is asking. One question I have is, what further constraints will Stripe provide on small-scale wave driving of the QBO?
Thanks. Great question. Looking at gravity waves is certainly something of small scales. It's something we're really excited about. And one of the things that our science team members who are interested in gravity waves, so including Joan Alexander, Martina Bramberger, Neil Hindley, and Laura Holt, have looked at is, what scales of gravity waves Strive will be able to resolve. And so on the right here is, you see the horizontal wavelength and vertical wavelength of gravity waves that drive stratospheric circulation. And, in the past, we've had observation of airs, which gives us, good sampling of horizontal wavelength, but only coarse vertical wavelength. Hurdles, shown in green here, looks more at shorter vertical wavelength, and Strive in blue will really encompass a much larger region. So we believe will really enable us to evaluate, the properties of gravity waves over a much wider range than previously possible.
And we have another question from Alex.
Yes, hello. Thanks a lot for a fantastic talk. It's obviously a very versatile concept, so I was wondering if there's a particular area that you're most excited in that Strife will contribute to.
Yeah, many areas are very exciting. For me, just for my own, sort of scientific interest, I'm really interested in convective outflow. I've looked at convective outflow from aircraft observations, which are, it gives us all these great detail, but it's, these are one-off. You see a convective outflow, and you can't really repeat that, right? You see snapshots. And so for me, being able to do that from having a global perspective and really constrain that aspect with composition, measurements of the composition of the outflow will be really exciting. In addition, we have now, NASA has this Falcon fleet, which includes, will include a LiDAR, a radar, also includes instruments like from Incus and Pulsar, so more on clouds and convective mass flux. So combining the information about what's going on with the clouds and formation of convection with observations of the convective outflow will be very exciting.
Thank you.
Yes, Johansson.
Yes, thank you. Thanks a lot for the nice talk. I have a rather technical question about the ATLAS instrument. I was wondering what spectral resolution or sampling will it achieve, and will you measure the whole spectral range of all the time, or will you focus on spectral ranges depending on the target for the orbit?
Yeah, so the spectral range is on the order of about 20 nanometers. It's a spectral resolution 20 nanometers. We'll measure the entire range. But for the retrieval of given species, we'll focus on specific wavelength, and these will depending on the altitude, because of various interferences, and we'll basically focus on the regions where we have the best signal. But the whole spectra is measured every time, so we can pick and choose where we'll have the best retrieval.
Thank you.
And we have another comment from Scott. He's writing, apologies if I missed this, but very briefly, is there a chance for pushing beyond the 3-year mission lifetime?
Yes, great question. So we're required to plan for 3 years. We designed the instrument so that it should be, and there's enough fuel, it should be able to last 15-20 years. And that's the way NASA does these missions. There's a prime mission lifetime, and then there's senior reviews that if the instrument performs well and continues to provide useful measurements, then it's renewed. And there are many examples of missions lasting much longer than their prime mission lifetime. And certainly it's something we hope that STRIVE will provide measurements for longer than these 3 years. But 3 years is the minimum requirement.
Thanks. So I think we now have no other questions. So yeah, thank you very much again for a great talk and discussion. Yeah, and if there's no other question, I think we can end this session and see you next time.
Thank you very much.
Thank
Bye.
you.
Thank you.
Bye.